Okay, I think we can get started now. So hello, everybody. Thank you so much for joining us for today's SEDS Online webinar. We're really happy to have you. My name is Chelsea, and I will be sort of leading you through today's talk by Fluid-sediment. I want to thank our sponsors, the IAS, for allowing us to offer all of these resources to you free of charge, all the webinars. You can see all of the recordings up on our website, as well as different types of teaching resources, things like recorded virtual field trips, things like that. So make sure and check it out on sedsonline.com. And today we are going to have a talk by Philip Staudigl. He did his bachelor's at University of Santa Cruz in California, another fellow Californian, so I'm happy to have him here. He then went over to University of Miami to do his PhD, where we overlapped for quite a few years in the same lab, so some more fun times there. After his PhD, he moved over to Cardiff University and was there for a few years before finally moving over to the University of Frankfurt last year for another postdoc position. And his research really sort of focuses on carbonate systems and really hinges, I guess, on carbonate isotope systems. So he's going to talk to us today all about that, and we look forward to hearing it. So Philip, I will give you the mic.
Thank you, Chelsea. I'm really happy to see so many people here. This is a big crowd. The talk that I'm going to be giving today is going to be largely focused on various projects that I've done in the course of my PhD and after, looking at the margin of Great Bahama Bank. And so the talk itself will be structured where I'm going to introduce you to the exact location that I'm going to be talking about carbonate diagenesis, specifically where it pertains to fluid-carbonate interaction. We're going to talk about some ways of constraining the recrystallization rate of carbonates using clumped isotopes, then how we can constrain different fluid advection velocities, and just the degree of open system diagenesis using calcium isotopes. And then lastly, we're going to apply these lessons to a different chemical system, and see if we can subtract the diagenetic signal or overprint on an existing carbonate record. So just to start, we're going to be talking about the Great Bahama Bank. We're specifically going to be looking at the leeward margin, which is the western side of it, which is largely shaped by these benthic currents which flow through the Santurn Channel and the Straits of Florida. This is a system which has evolved a great deal over time. It started out as a much smaller platform and then expanded over the course of the Miocene, where there was a steepening of the platform margin, and this was largely triggered by the onset of benthic currents in the area. This was talked about a great deal a few weeks ago by Gregor Eberle, who is the expert on this area. He gave a very good talk, which you can access online. And he basically showed how this margin evolves over time in response to winnowing by currents, slope stabilization via various processes. And he gave it a very, very, very thorough discussion. So I suggest, if you're curious about that, to see his talk. This margin is complex. Carbonate margins are very complex when it comes to fluid flow. Here we show a model which shows that as you sit at a sea level high stand, you can form brines on the platform interior, which then displace the fluids within the platform margin. And so whereas early in the system, you have thermal convection drawing in fluid from the platform margin, and then it flows into the interior, is warmed, and then brought out, expelled on the surface. But then as this brine sets in, it can slow the fluid. And so the lesson that we can learn is that fluid flow in these sorts of platform margins is very complex. So just to introduce you to the site that I'm going to be talking about mostly today, it's ODP site 1003, which was sampled in 1997 by the Ocean Drilling Program on leg 166. Which was co-chiefed by Gregor Eberle and Peter Swart, who was my PhD advisor. It was sampled on the platform margin at a depth of about 500 meters. It's just a few miles from the margin. It's very close to very shallow. So it's in that steep limb of the margin. And it samples through sediments from the earliest Miocene to the present day. And it documents this change in platform geometry quite nicely in its sediments. So we're interested in carbonate platforms for a number of reasons, but they can be quite complex if you want to treat them as an archive of ancient ocean chemistry. So if you have, here's a very good example of it. You have here in this blue site 525, this is a pelagic record. This is a more representative record of the marine system as a whole, whereas all of these other cores, which were taken from around the world, all show a considerable difference between their carbon isotope record and that recorded in the larger open marine system. So shallow carbonate records have sedimentary complexity to them, which makes them more complicated to apply as a geochemical record, but they can be, and these are the reasons that I just described. So you have a number of factors that make them more complex. You have different sediment sources. You have the platform sediment. You can have mixing between platform and pelagic sediments. Diagenesis is, of course, always an issue because, at least in the modern, shallow carbonates are made predominantly of metastable high magnesium calcite and aragonite, which will recrystallize quite readily over time. And all of these factors can change in response to global sea level, which is why you often can see correlated carbon isotope excursions in systems that are quite far away from each other. So the reason they're interesting to study is that pelagic records, which are, you could consider the gold standard for at least simplicity and ability to be understood, they are invariably subducted. And so they are not a suitable record for any sort of ancient system. So often these shallow marine carbonates are the only extant records we have of ancient seawater chemistry. So it's important for us to figure out how these different processes affect the chemistry. So we're going to be focusing today on the fluid-sediment reactive exchange. So this is chemical diagenesis. And this is usually facilitated by the dissolution of one mineral and precipitation of either the same mineral or another. So in this case, early diagenesis is often associated with the transition from aragonite to calcite. But deeper diagenesis can be driven by other factors, including differences in surface energy. You just have a process by which you have you go from finer grain sediment to coarser grain sediment, ending in a limestone. But what's important is that this is reactive exchange between sediments and corresponding porefluids. And so therefore, both of these systems can be affected by reactive exchange. So if you're dissolving a carbonate and you reprecipitate something with a different composition, conservation of mass says that whatever difference there is has to be taken up by the porefluids. And because of this, due to the different abundance of different elements in carbonate or in water, different isotope systems can be affected quite differently by rock buffering or fluid buffering. An example of this is here. So I take this cartoon where you have sediment exchanging with pore fluid, and then you have some lid on the system. You have some exchange with an outside source of water that is, let's say, seawater. And so if you have reaction that's faster than the exchange rate of than the residence time of the water in your system, you can saturate the fluids with respect to the element in question, and then that composition won't change over time. So here I'm showing three isotope systems. I'm showing carbon, which is the y-axis on both plots, versus oxygen and versus calcium isotopes. And you can see that depending on the ratio of the turnover time, so the residence time of seawater, which is tau, and the reactive term, which is R, you can have very different relationships between these isotope systems. And this is driven predominantly on the fact that there's different amounts of each element in the two media. So there's a lot more oxygen in water than say carbon, and that's because H2O, it's 80% oxygen by weight, but carbon is only a few millimoles per mole. So it's quite, or a few millimoles per kilogram of seawater. So it's far less water buffered. So that's considered to be a rock buffered element. And so in order to describe this system, you need to make a time integrated model that describes sediments throughout their entire burial history. But of course, this is a problem because sediments don't look like just this. They don't look like just carbonate and pore fluid with some exchange with outside media. You have layers and layers and layers of sediment. And so in order to describe this system, you have to create a depositional model which allows you to create new layers of sediment during the depositional history of the site. And then each of those packets of sediment is able to exchange either diffusively or advectively with their neighbors and reactively with the corresponding carbonate phase. And so this is a cartoon from a previous paper, which I published. This sort of highlights how this model is put together. But ultimately what this model is designed to do is to satisfy these two equations, where you have some concentration of some element, in this case that's C, in the fluids and solids. And the change of it over time is proportional to, in the fluids, a diffusive term, an advective term, and a reactive term. Whereas the solids are only affected by the reactive term, which is due to exchange with sediments. In this case, we're neglecting processes like bioturbation because in the models I'm showing today, it integrates over 30 meters, which is already far larger than any bioturbation effects that you're likely to see in this system. And so we just need to solve these terms. And what we need to do is solve, if we want to describe these systems over time, we have to understand the diffusive term, which is already fairly well understood just through analysis of pore fluids and experiments. You need to understand the advective term, and you need to understand this reactive term. And so we're going to start by looking and dissecting the reactive term. So if we want to constrain how fast sediments are recrystallizing, there's a number of methods at our disposal. So one is we could look at the mineralogy of the system. So we can show that the sediments lose all their aragonite by 200 meters, which corresponds to about 5 million years of age. And so based on that, we can estimate the reaction rate that's necessary for that. One problem with this approach is that it doesn't tell us if sediments are recrystallizing beyond that depth, because we've already lost our tracer. So if there's no more aragonite to convert, you can't study it, you can't constrain it any further. And so that necessarily is a limited estimate of recrystallization. Another system that's possible is looking at the abundance of elements in the pore fluids. And so here is a figure from my thesis, where we're looking at the abundance of strontium in it. And so the reason this works is because strontium is far more abundant in aragonite than it is in calcite. And so you can also estimate the reaction rate of aragonite to calcite just based on the expulsion of strontium from it, and then understanding the diffusive coefficient. And this estimate gives you another valid estimate, but again, it also is necessarily a minimum estimate because you reach the saturation state of strontium sulfate, which is a celestine. And because you've reached the saturation state, not all of the strontium is lost diffusively, which violates one of the assumptions in the model. So this is not a very, this is only a minimum estimate of recrystallization rate. So one method which I worked on in my PhD is the clumped isotope proxy. And so the reason this works in this, so if we look at the at this system from the perspective of temperature, you form sediments at warm temperature and recrystallize them at cooler temperatures. So you can apply this method of clumped isotopes to study how fast they're equilibrating to their new burial temperature. So you form your sediments at a fairly warm surface temperature. They're deposited on the margin and then are subsequently buried in the geothermal gradient. And so based on that, you can study the rate at which they're equilibrating to these new temperatures. So to apply this, we want to apply clumped isotopes to it in order to study how this system is recrystallizing and re-equilibrating. So just a primer, because I'm aware that this is the SEDS Online talk, not the geochemistry symposium. It's useful to give you a brief one-slide primer for this. So for any polyatomic mineral or material, there's different ways in which elements can be bonded to one another. So I'll give you an example here. So here we have 3 boxes of hydrogen, and they all have exactly the same ratio of hydrogen 2 to hydrogen 1, or deuterium to hydrogen. But if we start making actual molecules of hydrogen, there's a number of ways that we can bond these elements together. So first is a random distribution, where we have, it's just the likelihood of a given bond existing is just proportionate to the abundance of those elements. And so this is called the stochastic distribution. But then there's the alternative option, which is we bond only to like. So all isotopes are only paired with the same kind of isotope. And this is considered a clumped distribution. And then there's the opposite, which is that you're only bound to the opposite, and this is considered anti-clumped. So if we do this on CO2 that we react with, that we liberate from carbonate minerals, we can do the same sort of math, but instead of hydrogen, it's carbon and oxygen, and therefore we look at the abundance of mass 47, which is this clumped isotopologue. So this has a 13 carbon as opposed to a 12 carbon, bound to an oxygen 18 as opposed to just oxygen 16. So this is a clumped isotopologue. And if we measure this in carbonate, we can measure this parameter called delta 47, cap delta 47, which is the measured abundance of this clumped species versus the amount of it that you would expect based on a purely stochastic distribution. Now, the reason this is a paleothermometer is because there's this natural tendency towards isotope clumping, but this diminishes with heat. And so if we precipitate a carbonate mineral at different temperatures and then measure the delta 47 value for these minerals, we can calculate a relationship between the delta 47 parameter and the temperature at which the mineral formed. So if we measure the sediments at Great Bahama Bank, this is what we get. We have a record which shows some degree of variance, and it seems to have a signal at play. So how does this behavior reflect diagenesis? So if we take a look at this cartoon we have again, you start with your sediments, recording their primary temperature. That's the shallow, warm surface waters of the Bahamas. They're then deposited onto the margin, where they recrystallize at the benthic temperature, which is about 5 to 10 degrees Celsius. But then they're buried and progressively are buried in warmer and warmer temperatures due to the geothermal gradient. And so if you look at this system, you have a clear set of steps. So how do we turn this into recrystallization? And to do this, we need to do some modeling. So if we have a model for clumped isotopes re-equilibrating with depth, we just need to feed it some term, some function that can change over time. So here I have a relatively simple exponential decay function where you have your reaction rate at a given time is proportionate to some R naught term, which is just the initial rate of recrystallization. And then it's the sediment age with some decay term. And so in these models, they're all going to have basically the same parameters except the recrystallization rate. So here you have some initial recrystallization rate, but no lapse. So it gets to some equilibrium state, and then it just plays catch up with the geothermal gradient forever. Now, if we slow this down, it plays catch up forever, but then there's a certain excursion. There's a difference between the clumped isotope temperature and the actual current burial temperature. And you can see that this is actually proportionate to the rate of recrystallization. But then if we start adding these lapse terms to it, here we're showing the similar model as before, no lapse term, but now we decay it over 5 million years. So it slows down with a lapse rate of 5 million years and 10 million years. And what you see is that these clumped isotope temperatures start to record progressively more and more disequilibrated temperatures with respect to their current burial depth. And so if we then take this and account for the age depth, so the sedimentation rate over time. So those previous models were steady state. This model is not steady state because I allowed sedimentation rate to vary. You can then fit these terms, these reactive rate terms. Here I have them with different numbers, but with different letters, but it's the same. So you have an initial recrystallization rate of some value. In this case, it's about 0.7 recrystallizations per million year with a lapse rate of about 6 million years. And that seems to quite nicely fit the data that we measured on the Bahamian margin. And so with this function, we can actually now solve for the reaction term. So if we go back to this, this governing equation for fluid concentration, we largely know the diffusive term already. That's fairly well understood. There's many publications on how to model that. This reactive term, we've now constrained, but we're still in a bit of trouble with the advective term. So we don't know how fast fluids are flowing into or away from the margin. And this is still a problem if we want to come up with a descriptive diagenetic model for other systems. So it's necessary for us to figure out how fast fluids are flowing into the margin. And also, if this rate has changed over time. So in the modern, we have a number of ways of measuring this. So Henderson put out a study where they measured the abundance of different isotopes of uranium in the porefluids. And based on this, they were able to constrain the fluid flow rate to be about 10 centimeters per year in the present day. And then this is a very good snapshot for the modern, but as we know, that margins are quite complicated and can change dynamically in terms of how water is flowing into the carbonate platform. And so this value is not likely to have remained constant over time. And so now we introduce the other one of our two isotope proxies that we're focusing on today, which are calcium isotopes. And the reason why calcium isotopes are good is because unlike clumped isotopes, which cannot be rock buffered, you can always reset clumped isotopes. You can't easily reset calcium isotopes unless you have a large amount of fluid flowing through the rock. And this is just because in calcium's abundance in carbonate, it's about 10 moles per kilogram of calcium carbonate, but it's only 10 millimoles per kilogram in seawater. So that means that it's about 1,000 times as abundant in carbonate rocks as it is in seawater. And consequently, it's robust to alteration. So this is considered a rock buffered system. And it's understood well enough where we know that primary sediments, due to a variety of factors, fractionate calcium isotopes differently than the slower diagenetic reactions. So you have fewer kinetic isotope effects during diagenesis than you do during sediment formation. So the consequence of that is that diagenesis and primary sediment formation follow different rules, essentially. So fortunately for this site, in 2018, a data set was published for these calcium isotopes, and this is expressed as D44 calcium, which is the abundance of 44 calcium in the carbonate relative to seawater. Seawater is the standard that they're using here, and it's the one that we'll be using in this talk. So we have this data set for calcium isotopes, which is published. And so now we need to construct a depositional reaction diffusion model for calcium isotopes. And so we have these two governing equations. And because the diffusive term is largely known and the reactive term is known, and we know the final concentration of calcium isotopes in the solids, we can actually solve for the advective term. If we have a number of parameters for the model, so this is a table from the paper where this model was published, but we account for quite a few effects in this. And then what this model does is it takes these terms, it takes an assumption of what the advective velocity is, and then it outputs a downcore record for calcium isotopes. And so if you have no advection, this is the trend that you see. This is largely governed by the actual evolution of calcium isotopes of marine seawater since the Miocene. So there's a small change over that time. But if you start advecting water into the system, you have progressively more and more fluid-dominated, reaction-dominated calcium isotope records. But what's important is that these parameters don't describe the system very well. So no single advection rate can adequately describe calcium isotopes. And so the next question is can we solve for advection over time? So if we have some function where we can change the parameters over time, we can then use machine learning in order to solve for the optimum value. So what we've done here is we have, in this case, 7 points where you can change the advection rate. So right now it's just 1 centimeter per second over time for the entire depositional history. But what the algorithm can do is it can take any of these red dots and adjust it to any value. And then it will solve the entire system and optimize it for a best fit. So here it is. This is the actual solution. You can only see the big steps, but in between each large step in the algorithm, it takes a number of small steps where it feels out the space and then finds an optimum solution. And so now it arrives at some best fit value, but that is only one best fit, and it doesn't account for things like uncertainty in the fractionation of calcium isotopes during sediment formation or uncertainty in the actual measurement. So if we account for that, we can run Monte Carlo doing the same approach, but allowing for uncertainty. So we just repeat this process each time with a slightly different set of assumptions within the distribution that we assign it. So here in this next slide, we run the model 87 times in this case, each time with a slightly different set of assumptions for the data. So the data are allowed to have some noise, and the assumptions, for example, the fractionation of calcium isotopes in primary sediment formation is allowed to change. And so each of those different assumptions gives us some different output, but we can then average over all of them and get some sense of the uncertainty in the system. And what we see is fairly interesting, is that we see a sudden increase in fluid flow into the sediments occurring at about 12 million years in the past, after which it tends to be higher. You have more advection into the system after that. And this coincides with this change that I was talking about earlier in the platform geometry over that time, where at 12 million years, you suddenly start having drift deposits in the carbonate in the straits. So this is due to an increase in benthic currents, and you start seeing this steepening and progradation of the platform margin. And so what we're seeing here, the increase in fluid advection, is possibly due to winnowing of the finer grained sediments, meaning that you have a more permeable sediment forming, and also possibly due to the progradation of the margin, meaning you're closer to these systems of thermal convection on the platform interior. And it's difficult using this method to determine that. So modeling is fluid flow modeling would be a better approach than this. But what we've shown is that it does change. And for our purposes, that's what matters. An interesting note is that this change in benthic currents at the time is a largely globally synchronous event, where you start seeing drift deposits across on carbonate systems in every ocean, where you start forming drift deposits and having changes in the nature of carbonate platform, just carbonate system deposition. And so one thing worth noting is that you might expect similar changes, not necessarily in the same way, because every carbonate system responded differently to this change in benthic currents, but you would expect a change in the carbon record, in the carbonate records at this time, due to this rearrangement in benthic currents at that time. So we've now measured the advection rate. We have some quantifiable way of doing that. So now we've solved our problem. We've already constrained the diffusive term. We now have solved the advective term, and we've now solved the reactive term to this. So now, can we subtract diagenesis from a record? This is always, a contentious statement to make, and I certainly don't think that this is as simple as I'm applying it right now. But for the sake of just an academic exercise, let's see if we can. So going back to carbon isotopes, I showed these plots earlier. You have a series of shallow carbonates, which are these here that all seem to be trending off towards more positive values over time. And then you have your marine value, which is trending to be more negative over time, which is reflecting the global system. So if we look at one of these shallow sites, what is the contribution from local diagenetic effects? And can we then correct this record somewhat for diagenesis? So just looking at the modern system, reasons why this might change, why these records might change and why these shallow carbonates are so different is in part due to fractionation of carbon isotopes on the platform top. So you have this large shallow sea or shallow lagoonal area where you have photosynthesis occurring, and photosynthesis is slowly taking out the lighter carbon isotopes, which means that fairly rapidly you increase the carbon isotope ratio of the water on the platform top, meaning that carbonates forming from that site in that region have this enrichment. And there's also a number of other vital effects where you can do this. So the question that we're going to try and answer is, can we determine the fractionation of primary sediment, of pristine sediments over time? Just to show you what the record looks like, here in gray, I have the site that we're talking about here, that's site 1003. I also show an adjacent site that samples the drift deposits over time. And so that is a different site. But what we see is that it trends toward more negative, and then it's, towards the bottom of the core, it starts to look a bit more like seawater. And so the question is, how much of this record is due to diagenesis and how much of this is due to that? So we're going to be talking about this fractionation. So instead of carbon isotopes as a whole, I'm going to be talking about the fractionation of carbon isotopes relative to seawater. So this is just primary over the carbon isotope ratio of seawater. And this could reflect any number of any combination of these effects. And so here we have a reaction diffusion advection model for carbon isotopes. And here what I've done is we're applying the same machine learning technique as before, where we have now we have 20 control points, which the algorithm can tweak as necessary. Right now, they're all set to be approximately the modern value, which is about 4 per mil enrichment relative to seawater. And then we're going to let the algorithm find a more optimum solution over time. And this is currently correcting for all diagenesis based on these assumptions. So if we let the algorithm go, it starts to tweak. It tweaks the knobs until it settles on some optimum solution. It's a repeating give. And so it finds some value. And then now that we have this optimum value, again, we need to account for all of the a number of the uncertainties in the system. So what we do is we repeat this process using the same 87 repetitions that we did for calcium isotopes. So propagating those uncertainties into the carbon isotope space, we can then find optimum solutions for this alpha sediment value over time. And what we show is that it has changed considerably over time. So you have in the early Miocene, the carbon isotopes were fairly consistently fractionated relative to seawater. And then at about this 10 to 12 million year transition period, you start to see an increase in the fractionation of carbon isotopes. And so this could be any number of systems. So these older sediments were deposited more distal to the margin, which could be just effectively reducing the input of platform-derived sediment. But also this could reflect an evolution on the platform top itself, because if the platform is smaller due to the prograding platform margin, that means in the past it was smaller, and therefore you could have a more well-ventilated platform top, resulting in less photosynthetic fractionation of DIC on the platform. But both of these systems are likely, both of these explanations are likely true and contributed to some extent. So, and this is a largely consistent story, where in the Miocene, in the mid-Miocene, you had a smaller platform. This is a figure that shows a seismic transect across the entire modern Great Bahama Bank. And as you can see, in the Miocene, it was this fairly shallow ramp and a much smaller platform top. And then as it evolves, you have this expanding carbonate platform, which results in a more prolific carbonate factory. You're producing more sediment to be deposited on the margin, and that would then outcompete whatever pelagic input we're seeing at the site. And also you see this increase in fractionation on the platform top. And this prograding platform margin is also associated with the same transition that we saw in the advection rates, where you're prograding out closer to where site 1003 is, and you start showing more of this advection into the platform interior. So this is tells a consistent story at the very least. So just to summarize the process that we're doing here, just to take you through the workflow, we have a reaction diffusion and advection model, which can simulate a given isotope systematic over time, but it requires constraint on various terms, which can vary from site to site. So the diffusive term is understood and doesn't vary as much between sites, but the recrystallization rate does vary over time and is likely to have varied between sites. And so this recrystallization rate we can constrain using clumped isotopes, both in the shallow early recrystallization stages, as well as during deeper stages of diagenesis. We can see it keep up with the geothermal gradient. And so based on that, we can form an equation which describes the system well. Then, using either calcium isotopes or something similar, you can constrain for the advective term over time, and then you can feed those two terms into other systems and then describe it in the context of reaction, diffusion, and advective exchange. And then based on that, you can, if you're comfortable with it, subtract out the signal and calculate the primary value. But the result that you get from that is only as good as the assumptions you put in. So it either has to be a fairly simple system, or you just have to be comfortable with very large uncertainties in your result. And with that, I think I'm finished. So I'd like to thank you all for listening. And I've attached here the references for the data sets that we use the most. So I'd like to reference the paper by John Higgins, who is at Princeton, as well as the clumped isotope data, which was published as part of my dissertation. And the coupled clumped and calcium isotope was published last year in EPSL. The carbon isotope, so the clumped calcium carbon model, is as of yet unpublished. So if you wish to cite any of this, just go for the 2021 EPSL paper. And with that, I thank you.
All right, Philip, thank you so much for that great talk. Definitely a lot to sort of mull over, for me at least, but very interesting stuff. Anyone who's out there and has any questions, please go ahead and type those into the chat now so that I can read them all out. Once you're typing in your questions, please let us know where you are watching from. It's always interesting to see where our participants are located around the world. And yeah, so make sure and send them to everybody also, so that everybody can see the questions that you have. And so I will get this thing started. Philip, do you want to switch back to just any of the slides with your sort of the main equation where you have the different aspects that need to be worked out?
Yeah, I can do that. It's quite early to talk. Here we are. So here we have the fluid and solid term with some definitions and a cartoon of the model.
So just using sort of your, the schematic that you had of the ramp system, I'm just curious how, and I'm not sure if you mentioned this, but I might have missed it. So how much do these three terms or these three aspects, let's say, really differ based on where you are on that platform? And do possibly different places on the platform need different equations?
Yeah. Yes. So the equation itself is it's just a mass conservation equation. And so these terms can vary depending on the structure of the system. So the diffusive term is itself a function of porosity, of temperature, and then the velocity term can vary depending on where you are on the platform margin. And the reactive term, of course, is highly variable depending on sediment age, sediment chemistry, temperature, sediment location. And so here, instead of forming a model that predicts those values, we form a model that predicts the effects of those and then fits it with an equation. So if you wanted to create a more model that really solves everything, it would have to be much more complicated than the one that I'm using. But these systems, the different components of this change in their relative contribution all the time. And that competition is the reason why you see variance in chemistry of sediments based on where they're deposited.
Okay, so just to sort of, I guess, summarize or clarify for myself, all of these different terms, they are varying across the platform. They're varying with age, with what's going on in the system. And so, but in general, you're solving for one value for a given time. Is that correct?
Yes, and a given place. In this case, the place is site 1003 and the time is whatever point we are in the model. And so based on that, its burial depth gives you temperature, for example, and we know the porosity, the downpore porosity, we know the relative compaction rate of these sediments. And so based on that, we can estimate the diffusive parameter, for example, the diffusive coefficient. And then but then you need to solve all of these other values, for example.
Sure. All right, that sounds good. Oh, okay. So we just got a message that the chat was not on. So the chat is now working. So please, with your questions, send those through to everybody, and we will get to them. And while we're waiting, I'll sort of piggyback on my own question. So in terms of this modeling that you're doing, what could be the next step to make it even more in tune with the natural system? Would it be to sort of add more terms? Would it be to do these for specific places on the platform, or what do you think is sort of the next?
Well, what's needed? Because obviously, if I correct all of these records for Great Bahama Bank, the only thing we're ever going to get, if I correct the climate record for carbon isotopes, for example, if I do it for Great Bahama Bank, the only thing we're ever going to get from that is a value we already know. So we're never, it's Miocene sediment. I have better records of the Miocene. So why waste all this effort studying a system where at best I can only get a record that's worse than the modern value? And so the question is, what do we need to do in order to extrapolate this approach to an ancient system? Like if we, the Capitan Formation, if you want to go, to older systems, the question you need to answer is, can I create a similar model that would predict the effects over time on some ancient outcrop. And in order to do that, we have to much better constrain all of these terms and figure out how much they vary in modern systems. So by applying this method to other modern systems, maybe we can show the range of possible values for R, so recrystallization rate over age, and then figure out how advective terms change. And then we can, the holy grail of this entire project will be to be able to apply this sort of modeling approach to ancient systems in order to at least correct them somewhat for these kinds of early reactive exchange processes. And the reason why you want to correct for early diagenesis, because obviously these sediments also are buried a great deal. You realistically only can use the most rock buffered elements in ancient systems because they're mostly affected by shallow diagenesis, because that's where you have the most advection into the sediment. They're the most ventilated they're ever going to be, unless you start migrating, lots of groundwater through the system and you're in a more interesting depositional environment. But this early reactive exchange is what changes those terms. So like carbon isotopes. So by studying this in the modern, you can eventually form a system that you can then use to describe older records where you don't have a pelagic counterpart, for example.
Mm-hmm. Yeah, makes sense. Okay, our next question is from John Reimer, coming from Amsterdam. Hi, John. He says, thanks for the great talk. How will your model work out with shallow water carbonate platform cycles through time?
That is a very good question. So this site is on the platform margin, and it has never been subaerially exposed. So applying this sort of model to a system like the platform top, where you have fairly frequent subaerial exposure, this sort of a model isn't quite appropriate there, because you have, when it's subaerially exposed, huge volumes of water flowing through it due to meteoric facilitating meteoric diagenesis. And so it's better to have a different approach there, which approaches the chemistry from a more you can't account for the advection, for that kind of advection in this sort of a model. So it's better to just to have a model that describes meteoric diagenesis, more similar to the model that I showed earlier, which is just this open box system where you're flowing meteoric water through it, and then describe that system. But this model would be completely useless for describing a platform top, just because the assumptions in it doesn't allow for instance, vadose diagenesis or meteoric diagenesis. It could possibly do meteoric diagenesis if there was no vadose zone, but yeah, it would require a very different set of equations to describe.
For a platform through time. Okay.
Yeah.
So any other questions, please send them out. Yeah, John says, thanks for the extensive answer. Any other questions coming our way? I have a follow-up question for your summary slide. When is that last set going to come out? That last paper? Any predictions for that?
That's a main question. Well,
I'm just curious, out of interest of the subject.
Yeah. I mean, I'm more likely to apply this model to a novel data set. If a publication is going to come, it would be more likely from a novel data set that I would be producing. So it would have to probably wait till that, because this would be it's an interesting model, and if there is interest, I could write it up, but I'd be more interested in doing that as part of a more substantive publication.
Sure. All right, our next question is coming from Ross Campbell, coming from Kingston, Ontario. Says, thank you, Philip. That was a great explanation of the concept of clumped isotopes. I think I understand it a little bit better. And the modeling is interesting. Lithofacies, for instance, depositional environment, sediment source, etc., must play a role in the factors you've modeled. Any thoughts on that?
Yes. Absolutely correct. I tried to account for that in the carbon isotope model, where I let that be a free parameter. I just produced these models fairly recently, so I haven't had a chance to go through the actual sedimentary record for each of these sites. I did briefly show it in one of the earlier slides, where I compared the clumped isotopes to depositional facies. Let's see if I can find that. Maybe I didn't show that. I did show it relative to mineralogy, but you're correct that these parameters do change. And for instance, you do see this change in the relative contribution of platform derived versus pelagic derived. But just from the modeling approach that I'm doing, it doesn't take that information into account. Instead, what it does is it solves for the composition of the primary material. And then based on that, you could compare, for instance, this record here of quote unquote corrected carbon isotope ratios. You could then compare this to the lithofacies measured and described at that site by the sedimentologists on board. And you do see some correlation, like where you have positive excursions in this, you do actually see larger turbidites. So larger turbidites are associated with that. But it is hard to tell at this site. But this did account for things like depositional hiatuses. So if it's in the age depth record, it is accounted for directly in this model.
Okay, great. Our next question comes from Stephen, coming from Derby in the UK. And he says, sorry if this was already mentioned, but does salinity play a role?
Not directly. Salinity is accounted for because I account for the density. I have to account for the density of the water in these equations. And so salinity does play a factor in that. That is a problem that I was thinking of adding to this model, because if I solve, for instance, for if I apply this method to oxygen isotopes, for example, and I do this in the 2019 paper, I have more discussion on that. I don't have a figure, I'm afraid, but what we do show is that at depth, you have a positive excursion in oxygen isotopes that cannot be solely accounted for by diagenesis. And so this is possibly representing the presence of brine at that depth, where you have enrichment of delta 18 on the platform margin. Now, this interpretation is somewhat contentious because the delta 18 in the present day shows a positive excursion. However, it's not accompanied with a change in hydrogen isotopes, which you would expect in an evaporative brine. And so there is some debate in the present day if these deep-seated, if these saline water at depth with a positive oxygen isotope anomaly is due to evaporation on the margin or some other process, simply because there isn't a change in the hydrogen isotopes, because the oxygen isotopes can be affected by recrystallization, for example. So if you're recrystallizing at a different temperature, you exchange oxygen isotopes and can change the oxygen isotope ratio of the water.
Sure, yeah, that makes sense.
That's something that we discussed in the 2019 paper, but I didn't include that in the models that I'm showing today.
Yeah. Okay, and he just says, good to know. Thanks for the terrific presentation. Okay, our next question comes from Mohammed from Michigan. Thanks for the insightful talk. Does the model assume that the system is isochemical, meaning that there's no net dissolution or precipitation?
Yes, it does. That is one of the assumptions of the model, is that there is no net dissolution of carbonate at this depth.
Okay. Do you think that that is sort of a reasonable assumption at the depths that you've been calculating?
We're not seeing stylites. So, and in the most dramatic examples of carbonate dissolution aren't present at this site. Okay. We're not deep enough to start showing those sorts of large dissolution effects. As for deeper down, I think it's, you're not seeing huge amounts of dissolution. But it is possible that at these sorts of pressures, you do start seeing small amounts of dissolution. And that's something that my model does not account for, just through how it is. But it wouldn't be impossible to change the model to allow for that sort of process. But to do that, you would have to include in it a whole additional module for carbonate chemistry. And that's something that I'm working on with a smaller scale on projects with hydrothermal alteration of bivalve material that I'm doing with you, actually. We're working that into that model because that's a system where dissolution is very important. Not that it isn't important in this site, but in this case, these models assume that the dissolution flux is equal to the precipitation flux.
Yeah, okay, makes sense. Okay, our next question comes from Jin Tao, Chinese Academy of Science. Thanks for joining us. Thanks for your very amazing talk. Working on, oh yeah, he's coming from the Chinese Academy of Science, working on fluid inclusion, geochemistry. He's very interested in the application of clumped isotopes to detect paleo temperature of authigenic carbonate sediments, carbonate cements, filling the pores of tight sandstone. Can you give some suggestions for the preparation of this experiment? Is it possible to do clumped isotopes for authigenic carbonate minerals, filling in sort of the micron scale pores?
Yes, just to answer the first question, yes. In terms of the size of the pores, as long as you have carbonate present and as long as it's available for acidification, you can analyze the clumped isotopes in low carbonate siliciclastic rocks, for example. There are a number of problems that you can encounter doing that. This is, I did a project doing that sort of analysis on glacial diamictites and marine sediments in Antarctica. And one of the problems we faced, because we were trying to look at authigenic carbonates in these fairly low carbonate systems, is that we started seeing contamination from other minerals playing a role. But that didn't actually become a problem until you get down to about 2% carbonate by weight, at which point you start seeing enough sulfur in your system that you really don't want to put that near your mass spectrometer. It produces enough isobaric interferences to really break your mass spec for about a week if you analyze a bad sample. I can say that the people I did my PhD with were not fans of those samples. Yes, but if you're applying carbonate clumped isotopes to those sorts of systems, there's really nothing stopping you. It's actually more of an optimum system than the one I described here, simply because there is no, if you choose the right sediments, there is no primary carbonate. And so you don't have a primary signal to worry about. So it's purely the authigenic system.
Makes sense. So I guess you said something around 2%. So Jintao, I guess it depends on how many of those micron scale pores you have in your system.
Yes. And just grind it fine enough.
Yeah.
Before analysis.
Absolutely. Okay. Yep. Thank you for your answer. All right. Well, with that, I don't see any more questions coming in. So Philip, thank you so much for joining us today for SEDS Online webinar. We're very happy you were able to join us. Thank you everybody for coming and watching this presentation, and make sure and join us next week for our next SEDS Online webinar, Wednesday, same time, same place. And for all of you carbonate people out there, there is now the registration open for the Carbonate Forum. You can find that all on our website on sedsonline.com, and look for the tab for the Carbonate Forum. And you can find all of the information there. If you have any questions, feel free to reach out to the email addresses on that site. And yeah, Philip, thanks again. And we look forward to seeing everybody next week.